continue. Let me open the table of content first. Okay. We are still in chapter 19, patching faster translation, and still on homework measurement here. Let me open that. Okay. Yeah, we are still in this homework measurement section, basically trying to check the cost of, what is it called? The cost of accessing the page, but I'm not sure if my implementation is correct or not. Okay. Yeah, okay. Basically, what is it called? We have the trial as the input, right? And then do some iteration according to the trial, and also the total bits we have. So let me run that, I guess. Basically something like this. But the interesting part, when I remove this trial, something like this, and then compile that, wait until extra C2, okay, and then I think red string, okay, the TLP, okay, and then right, if I remove this, printf, the time become significantly higher. The difference becomes significantly higher. I'm not sure what's going on there. But it is something to consider, I guess. And now let's, okay, I guess check this node in the get set affinity. Okay, I need this one. Okay, after a call to set scanninity, the set of CPU on which the thread will actually run is the intersection of the set specified in the max argument and the set of CPUs actually present on the system. The system may further restrict the set of CPUs on which the thread runs if the CPU set mechanism described in CPU set is being used. This restriction on the actual set of the CPUs on which the kernel thread will run are silently imposed by the kernel. Okay. It The intersection. Okay. Set of CPU on which the thread will actually run is the intersection of the set specified in the max argument and the set of CPU actually present on the system. The system may further restrict the set of the CPU on which the threads run if the CPU set mechanism described in CPU set is being used. This restriction on the actual set of CPUs on which the thread will run are suddenly imposed by the kernel. Okay, there are various ways of determining the number of CPU available on the system, including inspecting content of proc CPU info using sysconf to obtain the value of the SGN processor conf and SGN processor ONLN. I assume this is online, maybe stand for online, but who knows. And inspecting the list of CPU directories under device system CPU. Get this description of the Linux scheduling scheme. Oh, as description of the Linux scheduling scheme. The Affinity Max is a per thread attribute that can be adjusted independently for each of the thread in a thread group. The value returned from a call to get TID can be passed in the argument PID, specifying PID as 0 will set the attribute for the calling thread, okay, and passing the value returned from a call to get PID will set the attribute for the main thread of the thread group. Oh, and then this one. If you are using the POSIX thread API, then use speed thread set affinity NP instead of get set affinity. I'm assuming this POSIX thread API is the speed thread here, maybe. So there is that. Okay. Where is it again? I kind of forgot where the set affinity. Oh, okay. Look like it is this one. Yeah, I'm assuming the pinning a thread is using this one. Okay, now let me check. Pinning thread. Oh. Set core pinning. Okay, in computer science, processor affinity, also called CPU pinning or gauge affinity, enable the binding and unbinding of a process or a thread to a central processing unit or CPU, or a range of CPU, so that the process or thread will execute only on designated CPU or CPUs rather than any CPU. Okay. The implication of cache affinity on processor scheduling for multi-program shared memory multiprocessor. Okay. Alright, there is that. Okay. Let's use this, I guess. CPU 0. Okay. This is macro, right? Maybe macro for manipulating CPU set. Okay. CPU 0 clear set so that it contains no CPU. Alright, first thing first, yeah, I need to use this one, CPU set T. Nothing, okay. Maybe from set affinity here. And what is it again? Normally this argument would be specified. Okay. I'm not sure. Can we check the size in GDP? Set T. Okay, no symbol. Okay. Well, let's assume it is here, I guess. Max. Okay, and then set. After we clear, we set the CPU. I can use 0, I guess. Okay, so we are using the 0 thread or something like that. And then affinity. Wait. Remove CPU from set. Okay. PID, CPU set size, CPU set max. Okay. Current thread, size of max. Okay. Then max, if it is equal -1, see on failure not even is returned and error is set to indicate the error. Okay. Yeah, because we only use this get affinity once, I don't think we need to put the line number information like this one. Okay. And then return. Yeah, let's use 42. Just a random number. Okay. Alright. Get set affinity. Let's see. Okay, right. Yeah, forgot this one. Define genus source. Oh, okay. And then include dot its. Okay. Right. One. Get affinity. Yeah, it's still the same regardless of the printf here, which is quite interesting. Okay. Even though we are depending into the thread 0, I guess. But yeah, I'm not sure if this is correct or not. I mean, we are initialize the array to 0, right? If we didn't do this, let's say 0 and then doing something like this maybe to check the scenario not initialize array element. I'm not sure if that is correct or not. Yeah, maybe not. Yeah, I don't see any difference there. Is this the correct implementation? I'm not sure. Okay. can you ensure the compiler does not remove the main loop? Run the script on different machine and gather some data. Yeah, I'm not sure this is correct or not. First time you access it will be very expensive due to initial access costs such as daemon shadowing. Will this affect your code and its timing? I mean, it depends on the size, I guess. But yeah, I'm not sure this is correct or not. Maybe it's not correct. Maybe. What if I use Database 100? These still look quite the same, I guess. Maybe we will see the difference with larger memory access. Yeah, I'm not sure. Okay, Yeah, for this homework, I'm still not sure how to measure the page access. Let me check. How to measure is it measure page fault? From a C program on Linux. In realm of system programming and high performance computing, understanding how your application interacts with memory is critical for optimizing performance. One key aspect of this interaction is page fault, event that occur when a process access a memory page not currently loaded in physical RAM. Page fault can introduce latency, especially if they require disk input-output major fault, making them a prime target for optimization. For developer working in C, whether on embedded system utilities or high throughput application, measuring page fault directly from within a program provides granular insight into memory behavior This block will guide you through the fundamental of Patch Vault. Okay. Explore Linux specific API to measure them programmatically and demonstrate hands-on application to integrate this metric into your C code. Okay. Get our usage. Okay. Yeah, I'm not sure if this is the same thing. Get our usage, resource usage statistic for a process or its children. It field for minor and major fault. Well, let me put this in the reference, I guess, in case I want to revisit this later on. Yeah, let's put this question here. Oh no, okay. Alright. Something like that. Okay. Yeah, for now let's implement this like this, which I'm not sure is correct or not. Maybe in the future I will revisit that. Maybe. Okay, so now let's try continue to chapter 20, advanced page table. Okay. Paging smaller table. Oh, okay. Alright. We now tackle. Wait. Okay. We now tackle the second problem that paging introduces. Page tables are too big and thus consume too much memory. Let's start out with a linear page table. Okay, if we take a look at the chapter 18, I guess there are two problems with paging. The page table might be too big, right? For example, where is it? This is the example of the page table with address space 16K and page size 1K, right? We have 15 page table entry, which means if we increase the address space, let's say we have the 32-bit address space. Oh yeah, we are gonna have a lot. of page table entry, right? Okay, if this one, I think this is 14-bit. Let me check. Alright, this is 14-bit. 14-bit address space with page size 1K already take us 16 page table entry. And imagine if we have 4 GB of address space with page size 1K. Yeah, that's gonna take a lot of page table entry. Okay, I'm kind of forgot how. Oh, okay. The exponent by subtract from the exponent. Imagine we have this 32-bit, right, address space, and 1K page, what is it called, 1K page size, to something like this. We subtract the exponent, right, and this is the, what is it called, the virtual page number. So we have around this much page table entry, right? For example, in this case, when we have address space 16K and page size 1K, we have an exponent of 14, right? 14-bit address space and 10-bit offset, I guess, something like that, for the page size. And then if we subtract it, 14 minus 10, we will get 4. So the total page in the page table is 2 power 4, which is 16. That's why we got this 16 page table entry. And now if we have 32-bit address space, it is 4 GB of address space and 1K page size, we will have, what is it called, 4 MB of page table entry, something like that. Yeah, that's a lot. And searching that might be too long, I guess, if the page table too big. And also, yeah, maybe storing that also gonna become a problem. And keep in mind, this is for what is it called? This is for one process. One process have 4 MB of page table entry. And if you have 2 process, then yeah, it's gonna add up really quickly. Okay. We now tackle the second problem that paging introduces. Page tables are too big and thus consume too much memory, right? Okay, so what is it called? chapter 19 here, tackling the problem, this one, the extra memory reference, right, by using gates for the virtual to physical address translation. And now we are taking a look at this problem. Page table might be too big. And cost a lot of memory, I guess. Too much memory. And might cost too much memory. Okay, let's start out with a linear page table. As you may recall, linear page table get pretty big, right? As mungkin a 32-bit address space to power 32 bytes, right? With 4 kilobyte to power 12 byte page. I think this is page size, and a 4-byte page table entry. An address space to size roughly 1 million virtual pages in it. Okay, multiply by the page table entry size, and you see that our page table is 4 megabyte in size. Right, see? This is only one page table for one process. Recall also, we usually have one page table for every process in the system. With 100 active process, not uncommon on a modern system, we will be allocating hundreds of megabytes of memory just for page table. As a result, we are in search of some techniques to reduce this heavy burden. There are a lot of them, so let's get going. Okay. We will be allocating hundreds of megabytes of memory just for page table. As a result, we are in search of some technique to reduce this heavy burden. There are a lot of them, so let's get going. But not before our crux. Okay, crux, how to make page table smaller. Simple array page table, usually called linear page table, are too big, taking up far too much memory. On typical system, how can we make page table smaller? What are the key ideas? What inefficiency arise as a result of this new data structure? Make page table smaller. What are the key ideas? What inefficiency arise as a result of this new data structure? Inefficiency. Okay, the trade-off, I guess. Alright, simple solution. Bigger page. Oh, this is section 20.1. Okay, we can use a bigger page. We could reduce the size of the page table. In one simple way, use bigger bits. Take our 32-bit address space again, but this time assume 16 kilobyte bits. We will thus have an 18-bit virtual page number plus a 14-bit offset. Right, this is the offset, the page size. Okay, assuming the same size for each page table entry for byte, same size. Okay, page table entry for byte. We now have to power 18 entries in our linear page table and thus a total size of 1 megabyte per page table. A factor of 4 reduction in size of the page table. Wait. To power 18 entries in our linear page table and thus a total size of 1 megabyte per page table. A factor of 4 reduction in size of the page table. Not surprisingly, the reduction exactly mirrors the factor of 4 increase in page size. The same size. For each table entry. Is this the page size? Entries in our, I think I get where this is coming, right? See, this is the 16 kilobyte, 32 minus 14, 18, right? 18-bit virtual page number. But where do we use this? Okay, entries. So this is the entries. One megabyte per page table. Are we like doing this maybe? Oh, for byte. Okay, not for kilobyte. Is that correct? Don't tell me something like this. Wait. Where do we get this one? Total size of 1 megabyte per page table. Per page table. Hold on, this is the entry, right? Oh, wait a minute. Don't tell me it is something like this. Oh, so this is the entry Okay, and each entry have 4 bytes. I'm assuming something like this. Assume this is one entry. This, what is it called? The size of the page table entry is 4 bytes. Okay. So that's why it is 1 megabyte per page table. And previously, okay, 32-bit address space, 4 kilobyte, what is it called? 4 kilobyte page size, and then 4 byte page table entry size. So we divide this, basically subtract the, what is it called? The exponent, right? Become, I think 10, oh sorry, 20. Okay, right. We got this 1 megabyte and then multiply that by 4. That's why we got 4 megabyte in size. For what is it called? For the page table, the size of the page table. Okay. Let's say we have 32-bit address space, 2 power 32, and page size, with, what is it, for kilobyte. Okay, 12, right. And then the page table entry size is 4 byte. The total, the size of page table is yeah, let me try something like this. 32 divided by 12. Okay. Alright. And then divide 2 power 12 multiplied by 4. Okay, what do we call this? The total of virtual bits. Is maybe something like this. The total of virtual page in the page table. This one, multiply by the page table. Oh, okay, not that one. Multiply by page table entry size. Like this. Okay, yeah, maybe something like this. Equal to this one. Okay. Alright, that is why the page table size is 4 megabyte here for this scenario. Okay, let me read this first. For reduction in size of the page table. Okay. Yeah, we still have the 32-bit address space, but we increase the page size here with the same page table entry size. Okay, which make the page table size 1 megabyte. Alright. For reduction in size of the page table. Not surprisingly, the reduction exactly mirrors the factor of 4 increase in page size. Right? The reduction exactly mirrors the factor of 4 increase in page size. 16 kilobyte instead of 4 kilobyte. So we increase the page size 4 times, maybe something like that. Where is it? I think, okay, 14-bit. This is the first one, right? 4 kilobyte, and then we increase that, okay, to become this one. So it's like maybe something like this. Okay, no, maybe not. Yeah, but we increase this to become the 16 kilobyte page size. Yeah, the factor of 4. What does this mean? The factor of 4. Is it like increasing? Oh, or maybe Okay. Alright, it's like we multiply the previous page size by 4. And well, it's also the reduction from the page size, or from the page table size, from 4 megabyte to 1 megabyte, right? Okay. If we increase the page size from 4 kilobyte to 16 kilobyte, by 4, we will reduce the page table size from 4 MB in previous example. From 4 megabyte to 1 megabyte. Alright. Okay. The major problem with this approach, however, is that big page lead to waste within each page. Yeah, the internal fragmentation, right? A problem known as internal fragmentation, as the waste is internal to the unit of allocation. So basically, if we didn't use the entire page, we will have fragmentation inside those pages, which we might not be able to use those fragments and causing the waste, because sometimes we need a contiguous space, right? Side by side memory. I think the example is this one. Let's say if we have the 5 kilobyte like this, this is 1, no, not that one, this is 2, and this is 3. But if, let's say, this is already been used and we need 10 kilobyte, even though this is what is it called, the total is 10 kilobyte, but we might not be able to use this because this is not contiguous. As far as I understand, that's what fragmentation in here means. So we are wasting this fragment, something like that. Okay, and then let me do the calculation again, I guess. Power 12, not power 12, power 14 multiplied by 4. Where is it? Okay, 1 megabyte. this is internal to the unit of allocation. Application tools end up allocating pages, but only using little bits and pieces of each, and memory quickly fills up with those overly large bits. Thus, most systems use relatively small page size. In the common case, 4 kilobyte as in x86 or 8 kilobyte as in SPARC v9. Our problem will not be solved so simply. Ls. Okay. Let me read the footnote first for this one. As you may recall, or indeed you might not. Right. This paging thing is getting out of control, no? Yes. That said, always make sure you understand the problem you are solving before moving on to the solution. Indeed, if you understand the problem, you can often derive the solution yourself. Here, the problem should be clear. Simple linear array page table are too big. Okay. Let me read the aside, I guess. Multiple page size. As an aside, do note that many architecture, for example, MIPS, SPARC, x86-64, now support multiple page size. Usually a small 4 kilobyte or 8 kilobyte page size is used. However, if a smart application requires it, a single large page, for example of size 4 megabyte, can be used for a specific portion of the address space. Enabling such application to place a frequently used and large data structure in such a space while consuming only a single translation loop aside buffer entry. Okay. Can be used for a specific portion of the address space. Enabling such application to place a frequently used and large data structure in such a space while consuming only a single TLP entry. This type of large page usage is common in database management system and other high-end commercial application. Okay. The main reason for multiple page size is not to save page table space. However, it is to reduce pressure on the TLP, enabling a program to access more of its address space without suffering from too many TLP miss. However, as researchers have shown, using multiple page size makes the operating system virtual memory manager notably more complex, and thus large pages are sometimes most easily used simply by exporting a new interface to application to request large pages directly. Large pages are sometimes most easily used simply by exporting a new interface to application to request large pages directly. Okay. So we can request large pages directly. Interesting. Yeah, but again it will cause fragmentation, so the best we can do is minimize that, I guess. Hello Ritis. Welcome. Are you preparing for an exam or something? No. I'm just learning for fun, I guess. I'm curious about operating system, so I'm reading this book, Operating System The Easy Piece, and currently on chapter 20, batching smaller tables. So yeah, I'm not preparing for exam or anything like that. Problem will not solve. Our problem will not be solved so simply. Hybrid approach. Batching and segment. Oh, interesting. Wait. Let me check the table of content. Bigger batch. Hybrid approach. Oh. And then there is this multi-level batch table. Inverted batch table. Okay. Swiping the batch table to this. Interesting. Alright, so I guess we will continue this section, hybrid approach, batching and segment, on the next session. So that's it for now. Thank you for watching and see you next time. Bye bye.